Hello and welcome. Proofs. A theorem is always of the form P implies Q. And we also use the format if P then Q. So basically you need to prove P implies Q. So Q is the conclusion, P is your assumption, is your hypothesis. So first we introduce direct proof. In direct proof, you need to assume P is true and prove Q is true. You assume P is true and you prove Q is true. Here's an example. If n is even, then n squared is even. So if I take n4, square it, I get 16 is even. I take n6, square it, I get 36 is even. So that's what I'm trying to prove for all integers n. Now here we go, we assume n is even, we need to prove n squared is even. So what do we have? We have n is even, we need to prove n squared is even. So n is even, this means n is of the form 2k, where k is an integer. So now n squared, I take 2k, square it, I get 4k squared, which is equal to 2 times 2k squared, and then if I call this L, I get this to be equals to 2L, which is an even number. Another example, if n is odd, then 5n plus 6 is odd. So now I am given an integer n which is odd, and I want to prove 5n plus 6 is odd. Okay, n is odd means n equals to 2k plus 1. K is an integer. So now I take this and substitute here. 5n plus 6 is equal to 5. 2k plus 1 plus 6. You get 2k, 10k plus 11. That's 2 times 5k plus 5 plus 1. And if I call this L, that would be 2L plus 1. You can call it C, K1, M, any name you want. And obviously that's odd number. Here's another example. We need to show the sum of two odd integers is even. So we need to always understand the question. So if I take two odd integers, say 5 and 7, I add them, I get 12, which is even. If I take 7 and 11, I get 18 is even. So now, your assumption, let A and B be odd integers, and I'm calling C to be A plus B. I need to prove C is even. So now here you can see this one here is your P, and this one here is your Q. And you try to prove P implies Q. Okay, proof, let's put A equals to 2k1 plus 1, B 2k2 plus 1. In these situations, k1 and k2 are in Z. Now, notice here, I did not put 2k plus 1 here and 2k plus 1 here. Otherwise, you will be adding a number to itself twice. So that's what some students do. So now I take these and add them. Straightforward, A plus B, 2k1 plus 1 plus 2k2 plus 1. Add them. I get 2 outside. K1 plus K2 plus 1 equals to 2L. So I call this here L. So obviously that is an even number. Example number 4. Show the sum of two rational numbers is rational. The sum of two rational numbers is rational. So now let x, y be rational numbers, and z is x plus y. We need to prove z is rational. Again, this is your P, and this is your Q. And you're trying to prove P implies Q. Proof. X is A over B, Y is C over D, A, B in Z, and B is different than 0. C, D in Z, and D is different than 0. This is really the definition of a rational number. Definition of a rational number. So you can't put Y here, A over B. So you're adding the same numbers to each others. So now let's find Z equal X plus Y, A over B plus C over D. Common denominator. You add them, and you see this is equal to P over Q. So I call this here P, and I call this here Q. So P over Q, and obviously P and Q are integers, and Q is different than 0. So we proved the sum of two rational numbers is rational. Example number 5. The product of two odd integers is odd. So if I take two odd integers, say 3 and 5, 3 times 5, 15 is odd. Take 5 and 7, 5 times 7 is 35 is odd. So I'm trying to understand the question. So now let A, B be odd integers, and C is the product of these two numbers. We need to prove C is odd. Again, A is 2k1 plus 1, B 2k2 plus 1. Different. So now you get C is equal to A times B. We multiply these two numbers together. You get 4k1, k2, 2k1, 2k2, and 1, 2k1, 2k2, and 1. Obviously, you can see that all these like a even plus and 1 here. So you get 2 outside here, 2k1, k2, plus k1 plus k2, plus 1. So again, I call all of this L. And that's 2L plus 1, and obviously that is an odd number. Example number 6. If n squared is even, then n is even. Okay, so what do we have? We have n squared is even, and we need to prove n is even. N squared is even means n squared is equal to 2k. You take the square root of both sides, n is equal to square root of 2k. And there's no way that you can write this in the form of 2L, where L is an integer. So the direct method does not work, fails. Example number 7. If 5n plus 6 is odd, then n is odd. Okay, so let's assume 5n plus 6 is odd, and we need to prove n is odd. Again, 5n plus 6 is odd, meaning 5n plus 6 is equal to 2k plus 1. I do some calculation. I find n is equal to 2 over 5k minus 1. And this cannot be written as 2l plus 1. So again, the direct method fails. Now, again, we go to the original statement here. If P then Q, P implies Q. This is the theorem that we are trying to prove. The direct proof, we assume P is true, and we prove Q is true. Now, the indirect proof by contradiction, proof by contraposition, they all are the same, and they're based on this. P implies Q is equivalent to not Q implies not P. And I advise you to go to my video on logic theory to get more information about this. So P implies Q is the same as not Q implies not P. So the indirect proof, here's how it is done. You assume Q is false. You assume Q is false, and either you get a contradiction or you prove P is false. Let's see how that goes. Here, we're going back to example 6. If n squared is even, then n is even. Okay, so I couldn't do it directly. I'm going to use now proof by contradiction or by contraposition. So let's assume n is odd. See, we assume the opposite of this. the negation of this. If n is odd, we need to prove n squared is odd. So we're proving this, not q implies not p. So if you prove n squared is odd, technically it's in contradiction with this because n squared is even, that's your assumption. So we're proving this now. N is odd, meaning n is equal to 2k plus 1. N squared, 2k plus 1 squared. 4k squared, 4k plus 1. You get 2 outside of these two numbers here, plus 1. And this, again, is of the form 2l plus 1, which means n squared is odd. So I proved not q implies not p, or if I look at n squared is odd, it's in contradiction with the assumption n squared is even at the very beginning. Example number 7, back to example number 7. If 5n plus 6 is odd, then n is odd, okay? So now we're going to say, suppose q is even. See, the negation of this. Assume n is even and prove 5n plus 6 is even. So n is even, n is equal to 2k. 5n plus 6, you replace here, 2k. 5, 2k plus 6, 2, 5k plus 3, 2l. Which is even. So we proved not q implies not p. Example number 8. Show if mn is even, then m or n must be even. If m times n is even, we need to show that m or n must be even. So now we're going to suppose m and m are odd. So the negation of this, here we're saying m or n must be even. So we're going to say suppose both of them are odd. So suppose m and n are odd. That's not q. That's not q. Then in example 5 above, we proved that the product of two odd integers is integer. So we don't have to do the proof again here. Then mn becomes what? Odd. Okay, m times n is odd, and it's even at the same time. See the contradiction? Example 9. This is a very traditional example, really interesting to see how the proof by contradiction is really implemented. We need to prove square root of 2 is irrational number. Irrational number means we cannot write it as a fraction. So how do we do that? We assume square root of 2 is rational, and let's get a contradiction. Here how it goes. We assume square root of 2 is rational, meaning square root of 2 is equal to a over b. A, b are integers, and b is different than 0. Now, we are assuming now that a over b in simple form, meaning a and b have no common factors except 1. And that's we can do that. So we simplified the fraction to its simple form. Okay? Now, this is what we have. I'm going to square both sides. So 2 is equal to a squared over b squared. Then a squared is equal to 2b squared. Then a squared obviously now is even, see, because it's 2 times something. Now a squared is even. In example 6 above, we proved if a squared is even, then a is even. So now we proved that a is even number. Okay, a is an even number, then I call a equals to 2k. So 2k squared is equal to 2b squared because a squared is equal to 2b squared. So 2k squared is equal to 2b squared because a squared is equal to 2b squared. So if I did, this would be 4k squared is simplified by 2. I get b squared to be equal to 2k squared. Now b squared is even number. B squared is even number, then b is even. So now look at that. B is even and a is even. This is in contradiction with this because we assume that a over b is in simple form. And that's why we got this contradiction, is because we assumed square root of 2 is rational. Then a square root of 2 must be irrational. Example number 10. Show if n cubed plus 5 is odd, then n is even. Okay, so this is p, this is a q, and obviously direct method is not going to work for you because there's an n cubed here. So let's assume n is odd. See, we assumed the opposite of this, a negation of this. Assume n is odd. We need to prove now n cubed plus 5 is odd. N cubed plus 5 is odd. Okay, so we're proving not q implies not p. Proof. N cubed plus 5 is equal to n times n times n plus 5. Now n is odd. N is odd. And in example 5, we proved that the product of two odd numbers is odd. So this is odd. Now you multiply this odd number by n, which is odd, you get an odd number. Now odd plus odd, odd plus odd is example 3 above is even. So we proved n cubed plus 5 is even. So we proved not q implies not p. Okay, to summarize, to prove p implies q, assume p is true and prove q is true. That's direct method. The indirect method, assume q is false and prove p is false or get a contradiction. Now do not, this is warning, many students, they make these mistakes. Do not assume q is true. If you start your proof by assuming q is true, I will not look at the proof because that's what you're asked to prove. You can't start from it. You're asked to prove q is true. You can say, let's assume q is true. And do not assume p is false. Do not assume p is false because that's your hypothesis. That's your assumption. So if you avoid these two mistakes, then you really can't go wrong because you are left with assume p is true and prove q is true, or assume q is false and prove p is false. Now here are some other examples where we use different techniques. Proof by cases. Example number 11, for all non-negative integers n, prove n cubed minus n mod 3 is equal to 0, meaning n cubed minus n is divisible by 3. Again, don't start any solution without understanding what is really being asked. N cubed minus n is divisible by 3. If I take 1, 1 minus 1 is 0, 0 is divisible by 3. If I take 2, that's understanding the problem, okay? If I take 2, 2 to the power 3 is 8 minus 2 is 6, is divisible by 3. If I take 3, 3 cubed is 27 minus 3 is 24, again is divisible by 3. That's what the understanding of the problem. And now I am asked to show that Pn is divisible by 3 for all n. Divisible by 3 for all n. That's what I need to prove now. So you can let Pn equals to n cubed minus n. Now, obviously, this is equal to n minus 1, n plus 1. See, this one here is n squared minus 1. So n minus 1, n plus 1. Now, you have three different cases here. If n mod 3 is 0, then Pn is divisible by 3. If n is divisible by 3, then the whole thing will be divisible by 3, obviously. If n mod 3 is 1, then n minus 1 mod 3 is 0. If the remainder of n, the division of n by 3 is 1, then n minus 1 is divisible by 3. If n mod 3 is equal to 2, then n plus 1, if you add to n1, you will get a multiple of 3. Then n plus 1 is a multiple of 3. So n plus 1 is a multiple of 3, the whole thing is a multiple of 3. Because now if you have n mod 3 is going to be either 0 or 1 or 2. The remainder of the division of n by 3 is either 0 or 1 or 2. If it's 0, then n is divisible by 3, then the whole thing will be divisible by 3. If the remainder is 1, then if you take from n, you take 1, you get a number that is divisible by 3. So n minus 1 divisible by 3, all of this will be divisible by 3. If n mod 3 is equal to 2, so if the remainder of the division is 2, then if you add to n1, you get a number that is divisible by 3. So when n plus 1 is divisible by 3, the whole thing will be divisible by 3. Here's another example where you need to use case-by-case basis. For all real numbers x and y, let's prove x plus y absolute value is less or equal than absolute value of x plus absolute value of y. That's called triangular inequality. Case 1, x positive and y positive, then x plus y, then this one, the absolute value of x plus y will be x plus y. The absolute value of x will be x, the absolute value of y will be y, and obviously the left-hand side is less or equal than the right-hand side. It's equal in this case. Now, if both are negative, then the left-hand side will be not minus x minus y, and the right-hand side will be minus x minus y. They're equal, and there's no problem. Now, if x is positive and y is negative, if x is positive and y is negative, so you have this situation right here, x is here and y is here, or you can have something like this, x is here and y is here. So this left-hand side, okay, you have another two possibilities here. Either the absolute value of y is greater or equal than x, like in this case here, the absolute value of y is from here to here is greater than this, or the absolute value of y is smaller than x. So the left-hand side is going to be, in this case here, minus y minus x. In this case here, it will be x plus y. And the right-hand side is x minus y. And you can see that the left-hand side is less or equal than the right-hand side. See, this one is negative y, that's negative y. So here you have negative x, here you have x. So this one is smaller than this. Here x is the same as x, and y is negative. So you subtract it from x a number, and while here you have x, you add it to x a number. So this will be less or equal than x minus y. So you really don't need to do case number 4, x less or equal than 0 and y greater or equal than 0. This is similar to case number 3. You don't have to do that. And this concludes end of proofs. Thank you, and see you later.